So welcome everyone to our Introduction to Network Instructor Training class this week. This is the week of 11/8/17. We're going to be looking at Chapter 7. I'm skipping past Chapter 6 because Chapter 6 is really just an introduction chapter on what the network layer is, dealing with network addressing, logical addressing, IPv4, IPv6. And I want to go ahead and jump forward and do Chapter 7 and then give you actually end up having 2 weeks before we meet again because next week I'm traveling Monday through Friday, and then I will be home the week before Thanksgiving, so we'll have our class meetings the week before Thanksgiving. For you, it will still be on Wednesday, and then I'll move my Thursday, which will be Thanksgiving itself, classes to Tuesday, so be aware of that. Be aware next week we will not have class meetings. If you need me, I will be available. I do have my email address. I will be checking email and everything. Just realize I'm 3 hours different from you. So if it takes me a little bit longer to respond, or if you send me an email at 8 o'clock in the morning, you probably won't get a response until around noon. Just to let you know that, because I'm going to be in California, not California. Golly, can't talk today. Before we get started, are there any questions on anything to this point? Because I want to go ahead and talk about Chapter 7, but I want to make sure we got anything cleared up. I think the actual chapter that you're supposed to be on for this week is Chapter 8, so we're pretty close to being on schedule. Be aware that we are trying to work towards getting done the second week of December. We should be pretty close to that. The one thing that I have to turn on for you that's not on is the final exam. I can only activate it for 1 week. So when we get towards the end of class, get within 2 weeks of class, I'll start activating that particular exam for every week and leave it on for you to take. So be aware of that. The other thing about this course I want to make you very aware of is you must be doing your labs in net labs. I must be seeing those hands-on labs completed. If you don't do them, then I'm not going to pass you through. It's just that simple. That's one of the big things I have is we must have proof that you're doing the hands-on labs, and I need to be seeing you do those in our NetLab system. So again, make sure you're doing all the hands-on labs that are listed in our module section. Do 1 to 2 packet tracers, and then you can, from there, do the chapter exams, do the final exam when we get there, final written exam, and you will have a hands-on exam, which we will do inside of NetLabs. And that particular hands-on exam is a lab that you can complete in there, so it's not that bad. I'll send that out with about 2 weeks to go in the class again. So, are there any questions of where we're going from here in terms of the class itself? All right, well, if there's not, let's talk about IP addresses. IP addresses are logical addresses, which basically means that there's nothing about the machine or device that determines what would have one address over another. Now remember, this is a stark contrast from physical addresses or data link addresses. Data link layer addresses are associated with a physical address burned into the network interface card. Logical addresses, the reason my machine is 10.100.x.something is because that's what they decided to make this particular subnet that they put the instructors on. There's no reason other than the fact that they decided that this building is the 10, actually it's 10.102. This building is the 10.102 subnet, or excuse me, set of networks. So I'm going to actually go in here and not really giving much away, showing you the internal IP addresses on my campus because everyone uses the same, well, almost everybody uses the 10 network RFC 1918 address. If I do an IP config, you will see that my IP address among my 10,000 tunnel adapters, from having everything from VMware workstation to the VirtualBox installed, you'll see that my IP address is 10.102.10.81. Now, this particular portion of the network, 10.102, the only reason that all the IP addresses in my building are 10.102 is because the admins on this campus decided that this building would be the 10.102.0.0/16 CIDR range. So in other words, a range of subnets that we're going to put and summarize to. And then I happen to be part of the 10 network, or excuse me, the 10 subnet, because they decided that's what we would be on as instructors. There's nothing physically that makes us the 10.102.x network other than the fact that someone said, hey, let's make this building that particular range of addresses. When we look at IPv4, when we look at IPv6, we are going to discuss both because the predominant version of logical addressing out there right now is IPv4. IPv4 is a 32-bit address space. It is, when we're looking at IPv4, we're looking at a 32-bit IP address space, which seems big, but it has already run out. It's gone, it's done, it's finished. The only reason that we do not have to use IPv6 right now for all of our endpoints is because of NAT, or network address translation, that we will discuss more as we move forward. 32-bit address space, it was broken originally down into multiple classes. We'll talk about those. But this address space is gone. There are more devices on the internet than this space can handle. For this reason, IPv4 is giving way to IPv6, and we'll talk a great deal about IPv6, which is a 128-bit address space, which technically is supposed to be able to give an IP address to every grain of sand on our planet, which would mean that it will never run out, right? Well, we said that about IPv4 too. So as soon as we got nanobots and every single nanobot has got an IP address, we will probably eventually be turned into brown goo, and the nanobots will eat us, and we won't really worry about IP addresses. But the other thing is there will eventually be a time when we need something besides IPv6, but it should be a long ways away. Remember something very simple. Computers are stupid. They know ones and zeros, on and off. Whereas we see 192, 168, something, something, dot, slash 624, and others, we see in dotted decimal. Computers see everything in binary. And so what they're going to do is take these 192.168.10.0 addresses, and they see them as this. And this is very important because it's also going to be how we will determine whether or not two hosts are on the same network and what network a host is on. And we'll use a process called ANDing to do that. But it's very important to teach your students that computers really are dumb. They don't know much other than ones and zeros, at this point anyway. Now down the road when we get to quantum computing and there's ones, zeros, and multiple states, who knows what's going to happen. But right now it's all ones and zeros. When we look at IPv4, we typically interact with it in what is called dotted decimal format. In other words, one decimal number dot decimal number dot decimal number dot decimal number. So 192.168.10.10. This is how we type it into the interface for Windows. This is how we type it into the interface for any of our routers and switches. But when we do this, the computer actually sees it as this binary number, and it's an octet. So an octet, how many arms does an octopus have? 8. How many sides an octagon got? 8. So an octet is a series of 8 bits. 8 times 4 is 32. So this shows you why this is a 32-bit number. Each one of these octets can be converted from a decimal to a binary, and we're going to show you how to do that. By the way, let me ask you, is this so basic that I can kind of skip through this? Do you all know this? Or do you want me to spend time on it, or are you just like, hey, I know this, move on?
I'm good with it, of course, Kelly, but it's...
Keisha and Gerald?
I'm good.
Okay, Keisha? I don't mind spending time on it, because one of the things I want you to be aware of...
I'm good.
This...
I know it.
Okay, this section and the section on subnetting, to me, this is the single most important section in all of Introduction to Networks. If you don't know how to subnet, if you don't know IP addresses, you might as well not apply for 99% of the networking jobs out there, because it is a fundamental skill that we must have in order to work on networks. Your students will freak out when they see things like this because they have no clue. This is math, and when they see math, they immediately, most of them immediately freak out. Mine do anyway. But this is how we look at our base 10 numbering system. And we have a base 10 numbering system because we have 10 fingers. If we had 6 fingers, we'd probably have a base 6 numbering system. But in our base 10 numbering system, the radix is 10, and a radix is 10, and then you have a position. So you have a ones position, you have a tens, a hundreds, and a thousands. So if each one of those positions, if they're actually filled in with one of the the values for that position, which for base 10 is 0 to 9, you can get a decimal number. So really, in other words, when we look real quickly here, if we look at the number 99, we're actually looking at 9 tens, 9 by 10s, okay, and 9 by 1s. So in other words, when we look at our positions, and I'm not typing very well today, folks, my hands aren't working great, a little cold. But if we have 9 in the tens position, which gives you 90, and 9 in the ones position, which gives you 9, and then 9 tens and 9 ones is 99. And that's how our base 10 numbering system works. Well, binary works exactly the same. It just uses a binary numbering system to where the radix is 2, and then the positions are 0 through 7, and that's 2 to the 0 power, which is 1, 2, 4, 8, 16, 32, 64, 128. And I'll go ahead and tell you, even though I know this very well, typically what I will do when I take a certification exam, before I ever start the exam, now they give you a few minutes that with your little board to put whatever you want on the board. I usually put, 2 to the 0, and I just write it out. But 2 to the 0, I put 1, 2, 4, 8. I go all the way up to 2 to the 14th normally. And that way I don't have to think about it. I can just look down and say, okay, 2 to the 10th is 10, 24, 128, 5, 12, 256, 5, 12, 10, 24, 40, 96. So I can very easily find it and see it and not have to figure it out. Teach students to do that, and it will help them when they take the certification exam. That way, when they don't have to try to figure it out on the fly and make a mistake. When we need the number 192, in other words, we're trying to find the decimal number 192. You look at your octet and you say, is the ones position on? Well, the answer will be no, because it's not an odd number. If it is an odd number, the ones position will be on. Is the 2 position on? Is the 0, 1, 2, 4, 8 all the way up? And really what we do to do this is we look and say, do I turn on the 128 position? If the answer is yes, can I subtract that from 192? The answer is yes. So I turn on that position. Then you would subtract 128 from that, would leave you at 64. And then you could say I can subtract 64 from 64, so that gives me 1. So 192 decimal is 11000000 in binary. Students will need to be able to convert from binary to decimal and decimal to binary. To convert from decimal to binary, you use the subtraction method. So you take your number and you say, can I subtract? Okay, can I subtract 128 from 192? If the answer is yes, you turn on that position, subtract it, and find out what's left over. And then you say, okay, what's left over? 64. Can I subtract 64 from 64? Yes. Then in this case, everything's left at 0. Our next octet, 168, we go 128, subtract that, leaves us with 48. Can I subtract 64 from 48? No, but can I subtract 32? Yes. And then you go on down through and subtract out that way, 40, not 48. And you subtract that on out. So to convert from binary to decimal, we use decimal to binary, we use the subtraction method. If we're going the other way, folks, if we're going to go from decimal to binary, we just talked about doing subtraction. Okay, so this is how we do it. If it's greater than 128, subtract it, turn it on, and then you just move forward, just like this. It's just a subtraction method. But if we're going the opposite way, if we're going from binary to decimal, and they're not showing you that on this one. Here's decimal to binary. But if you're going from binary to decimal, you add it up. In other words, you look at the decimal positions and you say, okay, I've got this 1, so the 128 is turned on, so it's 128 plus 64. Now see, there's nothing else left. That's 192. One thing I do teach my students is I teach them this chart. Obviously, that's 0, right? That is 128. That is 192. I wish I had $1 for every time I put a 0 or 1 on a sheet or on a board. I'd be long retired. $248. Oops, got tab. And I just continue out. 252. 1, 2, 3, 4, 5, 6, 7, 8. 254. And of course, all ones is 255. So you can see here that if you look at all the possible ranges of an octet, they are from 0 to 255, or 256 possible positions, because you do count the 0 positions, so 0 to 255. If students kind of commit this to memory, then they can very easily find if they need to convert or need to know what 242 is in binary. They know it's 1111110010. It's 240 plus 2, and so you can very quickly do some easy conversions using this system. The other thing that's kind of neat on this is it will help them when we get to subnetting to make sure that they know the ranges and what the total amount that is available in each octet. So pretty simple, easy to set up. Let me put this in here just to make sure I've got it listed. So if we are doing decimal to binary, use the subtraction method. I cannot talk today, folks, for some reason. Binary to decimal conversion, use the addition method. In other words, you add up the value of the positions turned on. Now, there's a binary game that you can go out there and actually go to the learning network at cisco.com and create an account and log in, and there's a game that lets you go through and do binary decimal conversions. Any questions about those? That's something a lot of people learn in just their basic networking course. Okay. Well, let's look at this. IP addresses, whether they're V4 or V6, have a network portion and a host portion. Okay. Now, we used to have a rule. We used to have a rule that stated that on an IP address, okay, the rule was the network, subnetwork, or host portion can never be all zeros, or all ones. However, we changed that a little bit because we started using subnetwork 0. So now we basically just say that in an IP address, the entire network portion or the entire host portion cannot be all zeros or all ones. What you're going to learn is that when the host portion of an address is all zeros, what is that? Anybody remember? When the host portion of an IP address is all zeros, what is it? Keisha?
The host portion?
If the host portion is all zeros, so in other words, when we look at this, if I put all these
that's the network
zeros,
address, isn't it?
exactly.
That's your
exactly
net
right.
ID, your wire ID.
The host portion is all zeros. That's
Yeah.
the network. That's the network or the subnetwork.
ID.
Yep, subnetwork ID. What if the host portion is all ones?
That's your broadcast.
Exactly. That is all ones. Then that is your network broadcast. Network / subnetwork broadcast ID. Very good. And by the way, that's why you can't have the host portion all ones or all zeros. We now can have subnetwork portion all zeros, but we don't typically have the network portion all zeros. So we got an IP address. We've got, now looking at this one, they've assumed something here. They've assumed a classful mask because this is a class C by default, but they've assumed that the first 3 octets are the network portion and the last octet is the host portion, which means there are 24 bits, 8 times 3, 24 bits in the network and 8 bits in the host. One of the things that you use, and actually the thing that is used to determine what portion is a network and what portion is a host, is the subnet mask. In fact, by definition, a subnet mask is used to determine what portion of an IP address is the host portion and what portion is the network portion. In a subnet mask, you put all ones in the network portion of the address. So when I do this, when I do 192.168.10.10, and I use the default mask of 255.255.255.0, I have put all ones in the mask for the first 3 octets. So this is saying that in the address above, the network portion is the first 3 octets. And in the final octet, where there are zeros, that is the host portion. Then default gateway will be the IP address of the router interface that's closest to you, or closest to your network, or actually on your network, and in the has an IP address assigned to it. So here's our mask, /24. By the way, where do you think they get those /24 numbers, or /30, or /26? That is simply the number of ones in the subnet mask. So 255.255.255 is represented in most documentation as /24 because there are 24 ones in the subnet mask. You will also see the way that a host will figure out what actual network it is on and what network a destination host is on is they take the IP address and they use a process called ANDing. And ANDing is a mathematical formula which, I know this is not actually what ANDing is, but for all purposes, it's the equivalent of multiplying the numbers together. So a 1 and a 1 is a 1, a 1 and a 0 is a 0, and a 0 and a 0 is a 0. So anything other than 1 and 1 is a 0. And again, it's not multiplication, it's ANDing. It's a different mathematical formula, but logically, that's the way it works out. So you end up a 1 and a 1 is a 1, a 0 and a 1 is a 0, 0, 0, 0, and 1 and 0, 0. What happens when you AND an address? So you take an address, you AND it to its subnet mask. What falls through, you will notice, is just the network portion. In other words, when I AND this 192.168.10.10 to its configured mask, the host finds out that it is actually on the 192.168.10.0 network. Now this is important because the way a host sends information to another host is they AND their IP address to their mask to find out what network or subnet they're on. They then take the destination address and AND it to the mask configured on the sending host, determine what network it is on. If those networks don't match, it has to send it to the default gateway. If those networks do match, then it can send it directly. So it may send out an ARP request, ARP reply, but otherwise it will, if it's not local, it will try to send it to the default gateway. So ANDing is an integral process of how two hosts in an IPv4, especially in IPv6 too, but IPv4 network work to figure out what subnet or network they're on. And we've got a couple of places in there where you can actually go through and do the ANDing process yourself. Are there any questions about the ANDing process? Nope. Okay.
So I did so Kelly, so basically,
go ahead.
Of course, it goes ahead and checks and see if it's on the same network. If once it realizes it's on the same network in that environment, and then if there's a switch that's involved that has a MAC address table, it'll send it to that given switch with the MAC address table, right? Because it's tied in for the as a connection in that LAN in that local area network.
Okay, that's a good, very good question. Let's assume that the host figures out that the destination is on the same network. The next thing it's got to do is remember, at that point, it knows it can send it directly. but this is at layer 3. So it still has to go down to layer 2 and build a frame. So the next thing the host is going to do is look in its local MAC address table and say, do I know the MAC address of the destination for this IP address? If the answer is yes, it's going to build a frame with the destination MAC address, source MAC address, the IP information packaged as data for the frame, CRC, and send it. And then at that point, it's up to the switch to look in its content addressable memory table to figure out, from the ingress port, what egress port it goes out, if it goes out any. Okay? If it does not have anything, so the host figures out it's on the local network, it goes to build a frame, but it figures out it does not have the MAC address in the local host table, it has to send out an ARP request and then wait for the local ARP reply, which if it's a local PC or local device, that ARP request should be answered by an ARP reply. So does that answer your question, Sedella?
Oh, yeah. I was making sure we had the same understanding.
Yep.
Okay.
Yep. All right. So here's prefix length. So again, the number of ones in your mask. You see /8 through /30. One of the things you will learn as far as for networks, you've always got to leave at least 2 host bits, because 1 bit is going to be the network ID, 1 bit's going to be the broadcast ID. If you've only got 2 host bits, we will learn that 2 to the 8, or 2 to the number of host bits minus 2, equals your number of usable hosts. Well, if there's only 2 host bits, 2 to the second power is 4, 4 minus 2 is 2. So you could not have only 1 bit, a /31, otherwise you would not be able to have any host. You will see, however, don't get confused by this, you will see in the route table /32s, which are local entries, which specify the IP address that's on an interface. That's a little different. That's really not a prefix length that's used for, I'll tell you about it. It's not used for routing between routers. It's used in the local route table. So be aware that /32 is for one particular IP address. Our prefixes are typically between /8 and /30 for our networks. So we got a network address. We've got the address is that address where all of the host bits are zeros. The first host address is the first address that does have all zeros or all ones in the host portion. The last doesn't have all ones or all zeros, and then the broadcast has all ones and zeros in the host portion. So let's take a peek at this. 192.168.10/24, that has all zeros in the host portion, so that's our network ID. .1 is the first usable, .254 is the last usable, and .255 is the broadcast. So this is how we get that formula that I gave you. In every network, it's what I say is 2 raised, let me find my little caret, 2 to the 8th power minus 2 equals number of host bits, number of hosts per subnet. And in this case, H equals number of host bits. In our example here, we would think we've got 8 bits, right? So 2 to the 8th power. Okay. What is that, by the way? 2 to the 8th power is 256.
254 minus 2.
Right. It's 256 minus 2, so it's 254. And the reason being, here's one address. There are actually 256 addresses in this network because there are 8 bits. But the first one is the network and the last one's the broadcast. That's where these 2 go away at. That's why we lose those 2 in every single subnet or network. So again, network address, first usable, last usable, and then all the way down to our broadcast. Now here's something that gets a little weird and something that's kind of hard to see and think about. But if I give you this address, let me do this. If I give you the address 172.16.255.0, okay, /16. Can I assign that to a host?
No. Well,
Is that a usable address?
No.
We got a couple no's. Okay.
I say no also.
Okay. Let's think about this.
It shouldn't be if the broadcast for that /16 shouldn't it be 2545 the broadcast address should be 172.16.254.255. But it's /16.
Okay. Well,
Or am I
let's
looking
think.
at it? Oh yeah, I'm looking at it incorrectly. So it should be 17. So I got you.
Let's examine this a second. This is a /16, which means you've got 16 bits that are the network portion, right? So what is the network address for this particular network?
16.0.0.
Correct. So that's the network, because you got to think about this. This is what's called a typical class B. So we've got 16 bits that are for the network and 16 bits that are for the host. All right? If you set all the host bits to zeros, you get your network ID, right? So here's our network. If you set all your host bits to ones, what would that be?
That's our right.
So there's your broadcast ID.
So the last usable.
So what's the first usable?
172.16.0.1.
Okay. What's the last usable?
172.16.255.254.
Correct.
So that's.
So tell me something. Looking at it now, it's 172.16.255.0/16A, an address you can assign to a PC or a host.
With that mask, yeah, because it falls within the range.
Bingo. It's perfectly normal. And here's how you can prove it. These are the 16 host bits, right? Let's convert them to binary. We're not worried about the 172.16 because we know that's the network portion. What is 255 in binary? 1, 2, 3, 4, 5, 6, 7, 8, right? And 0 is 1, 2, 3, 4, 5, 6, 7, 8. Are all 16 host bits ones? For the address 172.16.255.0.
Yeah.
Are all 16 host bits ones?
For the network bits, I'm sorry.
The answer is no.
No.
All 16 bits are not ones. So all your host bits are not ones. Are all your host bits zeros? No. This is a perfectly usable address. It falls right here in the middle of this usable range. Okay? Not technically dead in the middle, but it's in that range. So your 16 host bits right here, they're not all ones, they're not all zeros. This is a perfectly valid IP address to be assigned. Now, let's change this. How about now? Can you assign that IP address to a host?
No, you can't.
You'll get an error message when you try to assign that to a host. Because the last 8 bits, see now you got something totally different. First 24 bits are the network, correct?
Right.
The last 8 bits are the host. What are the host bits here? 1, 2, 3, 4, 5, 6, 7, 8. All the host bits are zeros. So that is actually the network ID or subnet ID. The first usable address will be 0.1. The last usable will be 0.254. And the broadcast would be 172.16.255.255. And we're going to learn this is a subnet of that major 172.16 network where we borrowed 8 bits. All right? Let's try another one. Could I assign that to a host?
No.
Correct. You cannot, because there are 16 host bits. Yep, there are 16 host bits, the last 2 octets, and they're all ones. So that's not allowed. Now let's change this slightly. Let's think about how we could change this. Let's do this /8. How about now? Is that a valid address to give to a host? Keisha says yes.
No.
Okay, why do you say no?
The last part of the address has all ones in it.
But it's only a /8. Only the first octet is the network. Everything else is host.
Right? So here's the thing to think about. /8 means that this is the network 10.0.0.0, right?
Mm-hmm.
Okay. So we've got 24 bits that are the host bits.
Oh, shit.
Are they all zeros?
No.
Nope. Are they all ones? Nope. So this is a valid IP address. You could assign this to a host. Because you have to look at it in terms of the prefix and all of the host bits. Okay? They're not all ones, they're not all zeros. Now, the second we change this prefix, then you can't give it to a host. Now, here's something that if you ever see something like this, is that a valid IP address?
Yeah, you can't tell without the Subnet Mask.
Bingo. Exactly. That's the correct answer, Keisha. The answer is we don't know because you didn't tell us what the prefix is. Now, if it says in the question, assuming a classful mask or assuming a default mask for the address, since this is a class A, which is 0 to 127, which 0 to 126 is what's usable in the first octet, if you assumed a classful class A address, yes, this would be usable. But the correct answer really is we don't know because we can't really know what the prefix is unless you tell us. So this is a concept that students find very hard, and that is realizing that it's all the host bits cannot be ones and all the host bits cannot be zeros. But now some of them can. You know, again, if I make this a /8, I've only got, 8 zeros of my 24 host bits, and I've only got 16 ones of my 24 host bits. But they're not all ones, and they're not all zeros. Real quick, is this one usable? Could I assign that to a host?
No, because in the last octet, there'll be all ones.
Exactly. You cannot send it. That's right. Because the last octet, this is telling me the first 3 octets are my network portion. The last octet is my host portion. And if this is true, then the host is all ones. So this is the broadcast address for this particular subnet. Very good. So that is what they're trying to get you to see here, is that the host portion cannot be all ones and it cannot be all zeros. But they don't really go into and start showing you multiple octets of different addresses. And there's why I'm doing that. And assigning static IP addresses to a host. Well, if you try to put in a network, it will bark at you. There are 2 ways to give a host an address. One is statically, and we typically do that for anything that needs a static address, like printers, servers, anything that we're not going to have dynamically assigned, although I do know with DHCP you can do a reservation. Since we don't usually do that, we just do static for servers and those things. DHCP is used for most of our clients, so that we do dynamic host configuration protocol. And we'll talk more about this as we move forward. We talk about our good old Aunt Dora, discover, offer, request, and acknowledgement, which are the 4 steps in DHCP. Okay. Just real quick, unicast 1-to-1, so it's from one host to another host. So 4.1 to 4.253. Broadcast is 1 to everybody, so that would be going out to that .255 or in the all ones in the host portion. And then multicast is a little different beast. It is 1 to some. And what we do is we actually join multicast groups. And it goes to everybody, well, and that's, I'm generalizing there because it depends on how your switches are set up, whether or not they're doing like IGMP snooping and all types of things. But by default, we consider that multicast goes out to every port, and then only the machines that are on that multicast group actually move the frame beyond layer 2. Everybody else drops it. So unicast 1-to-1, broadcast 1 to all, multicast 1 to some, or 1 to a specialized group. All right. I think here we're going to talk a bit about private versus public addresses. Now, I kind of joke with my students about you know, going to this dinner party. It's kind of like the dinner party in Harry Potter, where he brings in all the students. You go into this dinner party and somebody says, "Hey, tell me what you know about RFC 1918." Okay. This RFC is the RFC responsible for defining the private IPv4 addresses. These addresses were set aside to allow folks to address their internal networks and then use NAT to convert to a single public address or a pool of public addresses on the outside. These addresses and the subsequent use of NAT are the only reason we're not all running IPv6 already on everything we're doing. The blocks that were set aside are the 10.0.0/8 Class A network, okay? The 172.16 to 172.31 or /12, which is 16.00 to 31.255.255. So a group of is called Class B networks. And then the entire set of 255 Class Cs of the 192.168.0.0 range. All of these ranges right here are blocked by ISPs. They go in and put in access control lists that do not allow these routes or these particular IP addresses to be routed across the internet in any way, shape, form, or fashion. Now, as we move forward, you'll learn about GRE, and there's ways to make anything happen. But by default, ISPs will not allow these to go across the internet. So you cannot use them to connect your network to the internet. We will learn later about NAT and how we can actually convert or translate these public or these private addresses into routable public addresses, which is exactly what you're doing at home, because most of you probably have a 192.168.0/24 or a 192.168.100.0/24 on your internal network, and then your router at the edge is natting to a public address that's being handed out to your device. Okay. So other addresses that are out there, loopback 127.0.0.1. If you ping it, it proves that the IP stack is loaded and working. We also have a series of addresses, 169.254.0.0/16, which we call a PIPA, or automatic private IP addressing. These came out first when Windows 9.8.5 came out, I believe it was. And the first time I saw a 169 address, I thought someone had put a rogue DHCP server on my network. And what it was is the machines were trying to access the DHCP server and could not find one. This is used for everything Microsoft now. If you take two Xboxes and you hook them together over a switch and they don't have a DHCP server, they will automatically assign themselves a 169.254.x.x/16 number. And then there's also this test address, 192.0.2.0/24, and they are used for teaching and learning. And quite honestly, until they added that to these chapters, I had no clue that even existed, because that's what's supposed to be used for all network and testing examples and documentation on the network, on the internet. I think very few people know about this because they don't use them. They use all kinds of different stuff, but it is out there. Now, let's talk about legacy addressing versus our current classless addressing. Back in the old days, when they first come up with IP addresses, there were classes of addresses, and there still are technically classes of addresses. We just don't use them because we now just use prefixes. In the old days, though, we had roughly 5 classes. We had class A, B, C, D, and E. Class A, and to give you a quick overview of how these classes came about, they looked at the way that the binary fields broke down, and they used that to determine the classes. For instance, you're going to learn that class A is anything that in the first octet goes from 0 to 127. Well, from a binary standpoint, that is because it means that the first bit position is a 0. So as long as it's always a 0 in the first bit position, okay, you basically have the range of 1, 2, 3, 4, 5, 6, 7, 8. So that is obviously 0 up to 0, 1, 2, 3, 4, 5, 6, 7, 8, which is 127. So class A's were naturally formed or set aside by the binary fact that the first bit was a 0. Okay? Now, this is also why you would think the maximum number of networks, you say, well, there's 8 bits. Okay, the default mask is /8, right? So there should be 256 networks defined in this range of class A's. Well, the reason that is not true is because the first bit must be a 0, which means there's really only 7 bits available, and 2 to the 7th is 128. So that confused me for years and years and years. I'm like, well, it's a class A, it's /8, that means there's 8 bits in the first octet. There should be 256 networks. Why are there only 128? And then I realized, well, duh, the first bit position has to be a 0, so that cannot change. So there's only 7 bits that can be used for the actual networks, 2 to the 7th, 128. You'll notice this does leave 3 octets for the host, so 2 to the 24th is 16,777,212 minus 2, which will give us the number of usable hosts on each network. So class A's are a small number of networks with a ton of hosts on them. Not very useful, really, because no one's going to build a network that has 16 million hosts on it that's a flat network. We'll talk about subnetting this down the road and how we can make that work. We also had class B's. Now, class B's were based upon the mathematical function that the first octet has to start with 1, 0. So 1, 2, 3, 4, 5, 6, 7, 8, which we know converts to 128. And if it's 1, 0, 1, 2, 3, 4, 5, 6, okay, that's 220, excuse me, 191. 91. Because 110, all zeros is 192. So class B is anything in the first octet that is a 128 to 191, or that has the binary positions of 1, 0 set in the first octet. These have 16,384 networks. That's because you have 16 bits with 2 of them reserved, so it's 2 to the 14th power right here. And then there's 2 to the 16th power number of hosts, and that shows you the high order bits are 1, 0. Then if we continue on, you'll see that for class C's, it was 192 to 223, and that is 110. Okay, it's the first 3 high order bit positions, and it's 2 million networks of roughly 254 hosts, usable hosts. We then have class D, which is 224 to 239, that's for multicast. And then we have 240 through 255, which is class E, which is experimental and is reserved for testing. So we lost a bunch of addresses there too because of the way that they reserved addresses. Now, all that's fine and dandy, but classical addressing had its problems. The reason being, you know, at one point, crazy enough, Stanley Community College had its own public class A network range. I tried my best to get them to keep it and then sell it back, and they wouldn't. The ISP asked for it back, and they gave it back, even though we contractually had it as our own basically by contract we could keep it. We decided to give it back to them, and you know, in hindsight, who knows what that thing would have been worth eventually. But we were being good net citizens too, so that was a good thing. But classical addressing was wasteful. It required you to take and assign addresses in blocks that were bigger than what they needed to be assigned. It wasted a lot of addresses, and as a result, we decided, well, we didn't. everybody decided to go with a different scheme to where we're going to do classless. And we'll talk more about that as we move into the next chapter. We're going to look at it's not the class of address that matters, it's the prefix that matters. What time it is? I'm going to have to move through here pretty quick. Let me do this. Let me come back to IPv6 because I need to spend time on IPv6, but we're out of time for today's session. So let me come back to IPv6 next class, and you go ahead and start working on Chapter 7, Chapter 8, and we can go from there. How does that sound?
Sounds good.
Sounds good.
Sounds good. I'm going to stop sharing, and I'm going to stop my recording. And